In today's video, I'm presenting a geometry problem that is a little bit trickier than it looks. It says the following. Two sides of an isosceles triangle have lengths 18 and 41. What is the area of the triangle? All right. For some people, their first thought might be to just use 18 as the base and 41 as the height of the triangle, or vice versa, and try to find the area just using 1/2 base times height. But that doesn't quite work here because, well, neither 18 or 41 are necessarily the base in height. We have to be more careful with how we think about this problem. But we are given some valuable details that are going to help us figure out some more information that we need. Specifically, we know that we have an isosceles triangle, which means that two of the sides have the same length. Okay, with this in mind, that means there are two possibilities for this triangle. Like I've done in other geometry problems, I'm going to draw a sketch just to better visualize the situation. The first possibility is that two of the sides of this triangle have length 41, which would mean that the third side would have a length of 18. And the second possibility is that two of our sides have a length of 18 and the third side has a length of 41. And these triangles aren't drawn to scale, by the way. Okay, now what do we do? If you think about this closely, one of these triangles actually cannot exist. And it's actually going to be the second triangle right here. And this is from the triangle inequality. For any triangle, the sum of any two sides of that triangle has to be greater than the side length of the third side. The second triangle violates that because 18 plus 18 is 36, but 36 is less than 41. So since this triangle violates the triangle inequality, such a triangle where you have two sides that have a length of 18 and a third side that has a length of 41 does not exist. If we took a look at the first triangle we drew, well, this one does satisfy the triangle inequality. 41 plus 18 is going to be greater than 41, and then 41 plus 41 is going to be greater than 18, which tells us that this first triangle is the one we want to look at here in more detail. And then, we can just disregard this second possibility completely because, as we discussed, such a triangle with these side lengths cannot exist. Just cross this out and then take a closer look at this first triangle we drew here. All right, I just copied that first triangle down here and made it larger so it's easier to see. You can find the area of a triangle by taking 1/2 times base times height. So we'll want to find the value of the base and height of this triangle here. Well, the base will be 18, but now we have to think about what the height would be. The height would be the length from the top to the bottom of the triangle. All right, so this is still unknown. However, we can use a little bit of trigonometry to help us find this length. It just so happens that with this bisector that we created here, we form two right triangles. And so, we can use some formulas that we know regarding right triangles in order to find the lengths of missing sides. If we're splitting this triangle in half, then that means that here, this side has a length of 9. So we can just apply the Pythagorean theorem to find h. And this is based on this right triangle that I have created here, where one leg is length 9 and the hypotenuse is length 41. By applying the Pythagorean theorem, we get 9 squared plus h squared is equal to 41 squared. So by subtracting 9 squared from both sides, we get that h squared is equal to 41 squared minus 9 squared. At this point, you could just substitute 41 squared minus 9 squared in a calculator, and you might be thinking, 41 squared, how the heck am I even supposed to solve this quickly without a calculator? Since this problem was on a math competition where a calculator was not allowed, I'm going to just continue to solve this without a calculator, and you'll see how I do this. It's pretty cool, actually. Instead of trying to find 41 squared, I'm just going to note that we have something squared minus something squared. And these sorts of expressions are ones you see all the time in algebra. Specifically, this is the difference of squares form, right? So that means the right side is just going to be equal to 41 plus 9 times 41 minus 9. And now I'll write the difference of squares formula on the side in case you need a little refresher. I'm just going to keep going here. 41 plus 9 is 50. And 41 minus 9 is 32. And I'm going to do something that looks a little strange here at first. I'm going to write 50 as 2 times 25. And then I'm going to write 32 as 2 times 16. I know, it looks weird at first, but there's a method to my madness. Now I'm just going to do 2 times 2. I'm just going to multiply these two 2's together to get 4. So we're going to have 4 times 25 times 16 on the right side. On the left side, we still have h squared. To find h, we're just going to take the square root of both sides. And at this point, you may see why I rewrote the product on the right side the way I did. We now have a product of perfect squares, right? So then we just get, well, 2 times 5 times 4, which is 40. 40 is the height of the triangle here. And now that we found the height, we can now calculate the area. I'll say, so the area of this triangle is just going to be 1/2 times 18 times 40, which is, well, 1/2 times 18 is 9. So this is the same as 9 times 40 here, which is just 360. And yeah, that is the solution here. Were you able to get the right answer? Please let me know in the comments. If you have any other thoughts, suggestions, comments, just things you want to tell me, let me know those too. I will respond to all comments left in the comment section. But if not, I hope you enjoyed this fun little problem. Like I mentioned, it looks simple, but there are quite a few details you have to keep in mind here. So, with all of that said, I hope you enjoyed the video, and I will talk to you in the next one. Bye now. Hey guys, so after reviewing the recording, I realized that I went over a step a bit too quickly and didn't discuss it in enough detail. That's what I aim to do here. I drew an altitude from the top of the isosceles triangle all the way to the base, but I didn't really explain exactly why we ended up with the two congruent right triangles and how that allowed us to figure out some more information about the triangle. So that's what I'm going to do here. By definition of an altitude, which is this length here, we have two right angles that are formed at the other end. So by definition, we have these two right angles here. And then since we have an isosceles triangle, we do have these two congruent sides. With these two pieces of information, we have enough to prove congruency. We can use the hypotenuse leg congruence theorem, which states that if you have two right triangles that have a leg that's of the same length and they have the same hypotenuse, then the two triangles are congruent. That's satisfied in our case because these two triangles share this side length h, and they also have the same hypotenuse length, 41. So by the hypotenuse-leg congruence theorem, we know that these two triangles here are congruent. And since they're congruent, that tells us that this side length and this side length have to be the same. Since the sum of these side lengths is just the base of the larger triangle, which is 18, that means that these two smaller side lengths have to have a length of 9. And yeah, this is just a complete explanation of what I mentioned before when I originally drew that altitude. So yeah, that's all I wanted to mention and add. If you have any further comments, please let me know. Your feedback is always welcome. All right. Bye now.